Okay, so another set of examples. Integrate 1. The integral from 0 to 1 x squared plus x plus 1 over x plus 1 multiplied by x squared plus 1 dx. Here, you can't use substitution. You can't use by parts. You need to use partial fractions. So you pick x squared plus x plus 1 over x plus 1 x squared plus 1. And say this is a over x plus 1 plus bx plus c over x squared plus 1. Remember that whenever the denominator has power 2, the numerator will have x plus a constant. Whenever the denominator has power 2, the numerator will have an x and a constant. Then first step, we multiply throughout by the common denominator. Another thing. So this guy takes out that guy when multiplying this by this. So we'll have x squared plus x plus 1 is equal to, this guy takes out that part when multiplying those two. So we'll have a x squared plus 1 plus bx plus c multiplied by x plus 1. Yeah, that's the question. Then we expand, so we have x squared plus x plus 1 is equal to ax squared plus a plus bx squared plus bx plus cx plus c. So now we equate the x squared should be equal to ax squared plus bx squared, telling us that 1 should be equal to a plus b, the coefficients just. Then x should be equal to bx plus cx, telling us that 1 should be equal to b plus c. You just go for the coefficients. Hello?
It's I'm confused there. The a plus the first stage there.
Here you just
What did you
expand.
do?
What is a times x squared? We get ax squared. A times 1, we get a.
No, like the bx plus c. The bx plus c.
So remember that day when I'm looking at partial fraction, we said that the difference between the powers of x in the denominator and the powers of x in the numerator must always be 1. Since here x is power 1, the numerator there will be no x, it will be x power 0. Since here x is power 2, the numerator will have an x. And if there's an x, then there must be a constant. That's why we initiated the bx plus c there. Take note of that every time you're dealing with partial fractions of this kind. Okay. So where are we now? The constant 1 should be equal to A plus C. So we just bring it here, A plus C. So now we solve for these variables. If we go in the first one, you can solve for A in terms of B. So you get 1 minus B. So that one is A in the third one. You have 1 is equal to B plus C. And in the third one, we have 1 is equal to, where there's A here, you have 1 minus B. And then plus C. Take this one the other side. We'll get 0 is equal to negative B plus C, telling us that C is equal to B if this is taken the other side. Now, when C is equal to B, then we're almost done. We go to which equation? This one. We say, since we know that B is equal to C, so where is B, we'll put C. So we'll have 2C is equal to 1, telling us that C is equal to 1 over 2. So B, since they are equal, B also is 1 over 2. And since we know B and A depends on B, so we'll have A is equal to 1 minus 1 over 2, which is also 1 over 2. So we have found A, B, C. We go back to the partial, so it's going to be A is half, so we'll have 1 over 2 x plus 1. B is half, C is half, so we'll have 1 over 2, not necessarily 1. We'll have x plus 1 over the half 2 x squared plus 1. So they have done the factorization because it was half x plus half over x squared plus 1. So half is common.
The question.
Uh-huh.
Where is the 2x equals to 1 coming from? Oh, the 2c equals to 1.
Since we said here that C is equal to B, you take it this equation. Where there is B, you put C, since they are equal. So you have C plus C, you get 2C. But the equation is equal to 1 on the left.
Okay, thank you.
Then you factor out the half, you remain with x plus 1 inside, over x squared plus 1. This is the same as 1 over the 2 down, and then 1 is multiplying x, so you have x plus 1 there. Like that, and x squared plus 1. Okay, so now that we have this expression here, this one, representing this guy here. So to integrate that guy, we integrate this one. So say the integral from 0 to 1, we'll now do the integral of 1 over 2x plus 1 plus x plus 1 over 2x squared plus 1 dx. So since we can separate, we'll take the 1 over 2 and remain is 0 to 1, 1 over x plus 1 dx, plus we'll take the 1 over 2, these 2, and remain with x over x squared plus 1 dx, plus the 1 over 2, these 2, and remain with 1. That's dangerous. Remain with 1 over x squared plus 1 dx. So integrate now. The first piece is direct ln 1/2 ln x plus 1. Then we'll bring from 0 to 1. No problem. Plus the second thing, use substitution. So you let u be the denominator, x squared plus 1. Then du is equal to 2x dx. If you solve for dx, you'll get dx is equal to du over 2x. So when you substitute in the integral, I'll do it from here. Substitute in the integral, you have the integral of x over u du over 2x. Remember there's a half here. So the x and the x will cancel and the 2 go out. So you have 1/4 the integral du over u. When such a thing happens, we bring in ln. So we have 1/4 ln x squared plus 1. Now we just put brackets and not the modulus because x squared plus 1 will forever be positive for any value of x. I get it from 0 to 1 plus. Remember yesterday, we did the derivatives of trig inverse. And we had something which looked like this one. I've just forgotten which one was that. So let's remind ourselves. What's the derivative of arctan? Suppose y is equal to tan inverse.
So can you go back to the previous page?
Yeah, we'll go back after this. Don't worry, we're going back here. So y is equal to tan inverse. Then we have tan y is equal to x. Then differentiate y. So we have the derivative of tan is x squared. So we got x squared y, and then dy dx is equal to 1. Then divide by sec squared y, divide by sec squared y.
Sorry, sir, I didn't take a screenshot. Me, please.
Okay, we are going back there. That's what. We're still going to write on that board so you can get a screenshot.
Okay.
So dy dx is equal to 1 over sec squared y. But we know that from this identity, sine squared x plus cos squared x is equal to 1. If we divide throughout by cos, we divide by cos, we'll have sine over cos is tan squared. Cos over cos is 1. 1 over cos is sec. So because it's squared, it will be sec squared. Now here we have sec squared, meaning that we have 1 over tan squared y plus 1. This is the same as 1 over tan y squared plus 1. But we just said that tan y is x. So we'll have 1 over x squared plus 1 as a derivative of tan inverse. Tan inverse can be written as arctan. It's the same thing. Its derivative is 1 over x squared plus 1. So whenever we find 1 over x squared plus 1 to be integrated, we'll remember that we got here via differentiating arctan. So the only way back is to remember that there was arctan at some point. So that the integral of 1 over x squared plus 1 dx is going to be arctan x, the same as tan inverse x. Go back and say our integral is half tan inverse of x. We are still evaluating from 0 to 1. So we now evaluate. You bring 1, you have 1 over 2 ln 1 plus 1. Minus, you take 0, you have 1 over 2 ln 0 plus 1. Plus 1 over 4 ln, you bring 1, you get 1 plus 1. Minus, you bring 0, you get ln 1. 0 plus 1 is 1. Okay, let me put it 0 plus 1. Then plus, we're now dealing with tan inverse. So we have half tan inverse of 1 plus half or minus. Suppose minus now. Minus half tan inverse of 0. 1 plus 1 is 2. So we have half ln 2. Since it's positive, no need of modulus. Minus half ln 1 plus 1 over 4 ln 2 minus 1 over 4 ln 1. What is tan inverse of 1? What's tan inverse of 1, you guys? I've forgotten.
45.
5. But 5, which is what?
5 over 4.
5 over 2. 5 over 4. So since we already have a half multiplied by pi over 4, we're going to have pi over 8. So pi over 8 minus tan 0 is what? Tan inverse of 0 is 0, is it? Tan inverse of 0 is 0. So we add. This is giving us ln 1. Remember that we said that ln 1 is 0. We said ln n log a1 will always be 0 because the transition from log to exponential is via a power 0, but this can only be 1. So don't forget this. Whenever you have 1, whenever you have ln 1 or log 1, you get 0. So we have 0 here, we have 0 here. Then we add, common denominator is 4. 2 into 4, we get 2. So we have 2 ln 2 plus ln 2. This is going to give us, exactly. So this is going to give us 3 over 4.
Excuse me, sir. Excuse me.
Okay, yeah, it's good.
So in the exam, like, do they bring such questions, or it's mainly for concept checks?
Wait. This is the exam paper for 2009. Question 4. Question 4B. No, and when you're going for exam, you don't go there to play. That's why it's 3 hours. You go there to wait. Oh,
But some
yeah,
questions.
No, just this one's on.
it had good marks though. I think there were about 10 marks out of 20.
So I have a question.
Makes more sense.
Okay,
So I
let's
have a
finish.
question. So on the part that where there is x squared plus 1, yeah? If the square was distributed throughout the x plus 1, how would we have written the bx plus c expression?
Okay, just hold a bit. So this will be 3 over 2 ln 2 plus pi over 8. Like that. Then, yeah. So in the exam, they had asked that show that this integral is equal to this. So it's the same as asking you to integrate, because for you to reach here, for you to show, you must move. Don't worry, guys. This is a very, very easy question. It's not that it has looked long because I was explaining. So I was writing all these monologue. I went and wrote all this, but you already have this thing and you're not teaching anyone. So you just go direct to the solution. And you have the answer. So to be easy.
So can you go to the page where they are getting the tan x?
It's going to go to.
Okay. So you're going there. Now I go to the question about this part. So you're saying the part where is bx plus c over x squared plus 1. If it was what? Please come back. I didn't get the question.
So yes, I was asking that on the part where there's x squared plus 1, and you use the bx plus c over x squared plus 1. In a case where the square is distributed towards the x plus 1, how are we going to write that expression?
If it was x plus 1 squared.
Yes, if it was x plus 1 squared, yes.
So, okay, let's get back to our question and get it, then we'll have that expression. If it was x, so if it was x squared plus x plus 1 over x plus plus 1, suppose this is squared, then we'll just change the inside. Maybe we put something else here, x minus 1. So what would have done to this guy would have said, okay, this is a over x plus 1 plus b over x plus 1 squared plus c over x minus 1. So when the square is not directly for x, you take it as a linear, repeated linear. So you'd write it and write it again with the power now. There is a bit of difference there.
Right, I think.
Okay. Somebody would say that another example. Now we are going direct into the applications. No, before applications. There's a question here that is nice. This was 1, 2. Integrate ex sine x dx from 0 to pi. Another giant question. By parts is the only way here. And the choice is all yours. We let u be sine x and dv be e power x. Differentiate u, will get cos x dx. Integrate here, you get v is equal to ex. Then you substitute. This is going to be, so you need to be writing it in this form. So let's leave the limits, they may disturb us. We'll find them when we are done. So the integral of ex sine x dx is now uv is ex sine x minus v du minus v ex du is cos x dx. Again, we have seen that this guy requires another by parts. So you perform it, you let u be cos x and let the v be ex dx. Differentiate, get du is equal to negative sine x dx. Integrate, you get v is equal to ex. Then substitute, so we have ex sine x, this one, minus the integral of this guy is uv, which is ex cos x, minus the integral of v du. Now v is ex, du has a negative sine x, and then dx. Now we are tired of integrating. So we have seen something which looks like this thing we have here has appeared on the right. When such a thing happens, you stop integrating. You work out things. So this is ex sine x dx is equal to ex sine x. We're now expanding negative times ex cos x. We'll have minus ex cos x. Negative times negative, you get positive. Positive times negative, you get negative. The integral of ex sine x dx. But this thing is what we have on the left. So you can take this guy, the left, so that we'll have the integral of ex sine x dx plus the integral of ex sine x dx is equal to ex sine x minus ex cos x. Now, when two things are the same kind of adding, we get two of them. Ex sine x dx is equal to ex sine x minus ex cos x. And divide by 2, divide by 2. So now we have obtained that the integral from 0 to 1, from 0 to pi of ex sine x dx is equal to ex sine x minus ex cos x over 2. We just need the limits from 0 to pi. So now we substitute the limits. We start with pi. Where there's x, we take pi sine pi minus e pi cos pi over 2. The whole thing minus, we take 0, so e0 sine 0 minus e0 cos 0 over 2. This guy, sine pi is sine 1/8. Sine 1/8 is 0. So we have 0 e pi minus e pi cos pi is cos 1/8, which is negative 1 over 2 minus e0 is 1. Sine 0 is 0 minus e0 is 1. Cos 0 is 1 over 2. So here we get 0 e pi, that is 0. Negative times negative 1, we get positive e pi over 2. And then 1 times 0, that is 0. Then negative times negative, we get plus. Then there's only 1 on top over 2. I found the solution. Such questions also do exist in the exam. Another exam, a very short one. Example 3. Okay. Okay. Example 3. Okay, do the screenshot, we'll do it on the other page. Fast.
We're done.
Yeah, done. 3. Integrate from 0 to pi over 4.
Excuse me, sir. I'm asking if you can repeat the previous page.
You want the screenshot, is it?
Thank you, sir.
You are not done. You just question them. Tan squared x dx. To integrate tan is not a nice thing. More ways when it's squared. But we just saw this nice thing here. Where is it? This identity. This identity can also be written as tan squared x is the same as sec squared x minus 1. And we know that the derivative of tan, is sec squared. So the integral of sec squared is obviously tan x. So what we'll do is we'll change this. Say, okay, we don't want to integrate you in this form. We'll change you to sec squared x minus 1 dx. And then split from 0 to pi over 2.
So I have a question.
Ask.
Why does the limit become pi over 2 from pi over 4?
Oh, it's 2 pi over 4 is just a mistake there. So pi over 4. And then it's 2 pi over 4 here. Sec squared minus the integral from 0 to pi over 4, 1 dx. The integral of sec squared, we just say that is tan x from 0 to pi over 4. Minus the integral of 1 is x from 0 to pi over 4. When you put pi over 4 where there is x here, we have tan pi over 4 minus tan 0 minus pi over 4 itself minus 0. Tan pi over 4 is 1. Tan 0 is 0. So go straight to minus pi over 4. This is our solution. Very easy. Just about the identity. If you know the identity, then you're doing fine. Without identities, no winner here. An exercise. You discuss in the group. When you get it correct, you post your friends. Integrate from 0. Let's change the limit to make it a bit nice. From negative pi to 0. We integrate ex sine x. We did sine. Now I want cos. Ex cos x dx. Yeah, this one is that you practice, and when you're happy that you have gotten it, you post in the group. Another one, I can make them 2. Another one is from 1 to 2, x multiplied by x minus 1 to the power 15 of the x. They are 2 now. Log out and log back quickly.
Sir, sorry, can I see the first code first?
What do you mean the first? First as in board 1.
Yes, like board 1.
Yeah.
Okay. Thank you.
Where's the last one?